name is Guozhang Wang, and I'm an engineer at Confluent and a PMC member of Kafka. And today I'm going to talk about Kafka and the rise of stream processing. So you see that we have two keywords here in my title, Kafka and the stream processing. And I would like to start with the second keyword and ask a question about what is not stream processing. Okay, the claim I want to make here is that stream processing is not necessarily transient, approximate, or lossy. Although we have actually seen multiple, papers or systems from literature as well as industry talking about like one-pass algorithms in stream processing, or how you can make, at least once delivery in stream processing. My claim here is that it's not necessarily the case that you need some batch processing as a safety net against stream processing. To me, stream processing is just a new programming diagram where you treat your input data not as a finite data set, but as a continuous data streams that you process them as soon as they occur. So to illustrate this idea of stream processing as a new programming paradigm, I would like to go through some of the commonly known programming paradigms. The first one is request and response. Right? This is a pure synchronous programming model where you send one input at a time as a request to your servers, and the server respond with an output. Right? So this is like one input and one output out. If you want to scale out such model, of course, you have to scale out the number of services because of this synchronous programming pattern that you had with request and response. And on the other extreme of the programming, you have batch processing. Right? In batch processing, you don't have this synchronous processing model, but instead, you will wait for a batch of inputs to be available, and then you send them to your computers or to your servers, and after a while, all your outputs become available. Right? It not only gives you like high performance, but also gives you this nice decoupling from where you generate your input data to where you start to process and consume them. But one other side of this issue is that you now have this latency from where the data was originally created to when the data was being processed, because you need to wait the whole batch to be completed. So stream processing, personally, I view it as something that sits in between of two extreme models, where at the same time, it is also an asynchronous programming model. You don't have like one input and one output. But on the other side, you also bring your data to your computers instead of wait for your data to be complete before you start processing them, right? So you can have like each one of your input can be one or more input points, and they can be processed as soon as they become available to your computers. And in such a programming model, there are a couple of very important trade-off decisions that users usually need to make, like latency, cost, and correctness. For example, if you are building an online building system in terms of against a log processing system, you may want to actually pay more attention to your correctness to have very accurate results, and you may actually be willing to pay more cost for that. And similarly, if you are building a real-time alert system, you may actually pay more attention into latency. But if you are building a ETL process system, you may not be paying too much in terms of that. So the one essence of streaming processing is that it should allow users to have the flexibility to specify those different trade-off dimensions while developing their real-time tasks. So just a very first recap of what is stream processing. I think stream processing is just a new programming paradigm that brings computations to unbounded data instead of bring data to computations. And it has trade-off between latency, correctness, and cost. So if you can leave my talk with a couple of takeaways, I hope this one will be the first takeaway that you can take. So now let's go back to the first keyword. Why is Kafka in this big picture of stream processing, right? And to answer that, I would like to ask a slightly different question. And what is Kafka really? If you ask different people who is already using Kafka or who at least have heard about Kafka, they may actually give you different answers. Someone may tell you actually Kafka is like a scalable pub sub messaging system. But sometimes they told you it's like a real-time data pipeline to solve a very common problem where you want to make your data that is generated from point A, which is like your online servers or your online data stores, to be available to be processed as soon as possible in another point. And sometimes they treat Kafka as like a distributed and replicated log where you can actually build your online storage and have like geo-replications using Kafka as its underlying replication layer. And sometimes you also heard people talking about Kafka as a unified data integration stack as against to like the so-called Lambda architecture where you can use it as a persistent buffer so that you don't need to have like complicated two-layer systems to build your software stack, but can just use Kafka as a source of truth to pipe your streams of data. So which one of those definitions is correct? And my answer is that it's actually all of them. Kafka, you can think of it as a streaming platform which you can not only publish and subscribe your records as data streams into and out of it, and you can also use it to store those streams of records as a source of truth, but also to process them and react to them as soon as those streams of records become available in Kafka. And today I will focus on the process story of Kafka and then drill deeper into what is really Kafka for stream processing. Okay, so when we talk about stream processing with Kafka, there are sort of like common practices already existing with it. The first option is you call the DIY option, where you can actually use the producer and consumer client of Kafka to process your data while using consumers to fetch them in real time. And after the data is transformed, is cleaned, or is enriched, you can then use a producer to send them back to Kafka or to any other third-party systems. But the DIY stream processing is hard, right? You not only have to consider how you can code your processing logic, you also need to consider other issues like how you deliver ordering, how you do state management, and how you do partitioning and scalability. All kinds of those hard issues, right? So the second option is that you can actually use a layered architecture and use a full-fledged stream processing framework on top of Kafka, which will basically handle all those detailed legworks for you so that programmers can just focus on their computational logic. And examples of those frameworks like Storm, Spark, Flink, or Samza, right? The list can go on. And one common problem, I would say, for those frameworks is that they actually can be another layer on top of Kafka, which requires you to build up those clusters in order to process your data. And different of those systems have their own specs in terms of how you configure your stream processing frameworks, how you leverage on resource management. Are you bound to use YARN or mesos? And how you actually can deploy such systems along with Kafka in your software stack. So you may ask this question, okay, I want to have this full-fledged system, but can I actually just customize my own management or configs to do those kind of processing? So here comes the third option that I want to talk about today, which is we have a lightweight stream processing library, just like the producer and consumer client libraries, which actually allow you to deploy your real-time applications using those libraries, just like the way you deploy your web servers using the producer or consumer libraries, and still have the powerful functionalities to do all kinds of stream processing tasks. So the Kafka Streams, which is a third client library besides the producer and consumer, which is introduced in the 0.10 version, which is, I think, this August, is just such like a library which is powerful and yet easy to use. This is part of the Apache Kafka project, and it has all kinds of different features like event-at-a-time processing, state management, and distributed and fault tolerance. And I will talk about details about those features. And it can be actually deployed in any way. You can go up to a data center using your favorite deployment model, or you can just run it in your own laptop, just like a normal Java application. And again, just like what you have experienced with your other Kafka clients like producer and consumer, you can just use Kafka Stream client as the same way to just depend on this library and start coding your applications with it. And you can use different kinds of resource management, and from the very uncool to very cool frameworks. By the way, this spectrum is purely dependent on the personal preference of my teammate, Michael. So if you have strong feelings against this spectrum, I can give you his contact information, and you can talk to him about that. The key point of the library of Kafka Streams is that we believe the simple is beautiful, right? You don't want to have a very not only a very powerful programming model, but yet it has to be very simple to use in terms of programming, but also for operations. So this is the DSL. I will maybe only take very few minutes to talk about the programming model of it. But here it is the DSL of Kafka Streams. You can create a source stream by reading from a specific Kafka topic. Here, for example, topic 1. And then you can transform these streams and create new ones, like aggregations, filtering, joins. And then eventually, you can send your result streams back into Kafka, or you can actually send those result streams into some other third-party systems as well. And finally, just like the way you will start your producer clients, you can then start your streams client with the specified computational logic as well as the configuration, and start them as a normal Java application. So that is all I want to talk about programming, right? Now I want to drill deep into how you actually will make operations of Kafka Streams, because we believe that API and coding is just one part of the whole story. You also need to pay much attention in terms of how you would debug your programs, how you troubleshoot when they have issues. And again, here we believe that simple is beautiful. The key idea of Kafka Streams is that it will try to leverage the Kafka brokers as much as possible to solve those difficult problems. And for those of you who are not familiar with the Kafka broker internals, here is a very quick overview of Kafka itself. So Kafka brokers store your data as a log, where messages are appended into the tail of the log by the producer, and the consumers can then start reading from the log based on their logical offsets as they are appended. So both of the reads and writes are sequential on your persistent disks. And in terms of scalability, we can then partition your logs into different shards, or we call it partitions, and have different broker machines to host those partitions, so that when you want to scale your Kafka brokers, you can just add more machines into your Kafka cluster, and then further partition your topics to be produced and consumed by more and more of those clients. So the Kafka streams leverage on the Kafka brokers such that it defines a stream just like a key value pair of a stream of key value pair records, and you can see that each one of these records can correspond to a message in the remote Kafka brokers. And when you specify your computational logic, the Kafka Stream library is internally building this computational logic as a DAG. We call it the processor topology. And each DAG has dots that is connected by those streams as key value records. And then each of those dots, we call them as stream processors. And when you specify your logic using the DSL, such a DAG is automatically constructed when you specify different steps by transforming your input and the intermediate streams, and finally, you send them back to Kafka. There are two special types of processors in the topology. The source processor is only used for reading data from the Kafka brokers. They don't have any so-called income streams or parent processors, because they are only piping data from Kafka to the downstream processors. And the sync processor, on the other hand, only have income streams but no outcome streams, because they are used to pipe data back into Kafka as well. So when you run your Kafka Streams application, the source processors will continuously pipe data from the Kafka logs. The records will traverse the whole topology, and eventually the sync processor will send them back into Kafka logs. And you can run your Kafka streams either co-located with the brokers, but more commonly, they will be running on 2 different machines, just like the way you run your producer and consumer clients. And then if you want to scale your Kafka streams application, the easiest way is that you can just start the same piece of code of Kafka streams on 2 different threads or 2 different machines, and they will actually automatically balance the work by assigning different partitions of their input topics to different instances of those applications. And when you want to scale up your application, you can simply add more partitions into your input topics, and then start the same piece of code on more threads or machines, which can then pipe data from those added partitions as well. So the next topic I want to talk about is how you manage your states in a stream processing application. There are 2 kinds of operators in stream processing, right? You have filter, you have map, or you have flat map. All of them are so-called stateless operations. You have 1 input and you have 1 output, or multiple ones, but you don't keep record of the recent ones. And there are other stateful operators like joins and aggregations, whereas you need some kind of a state store to keep track of those intermediate results in order to complete such computational operators. And in practice, people usually have 2 strategies to basically establish those state stores. One option is that you can actually use some remote stores where your stream processors will basically talk to them while they need to read or write data to those stores. But of course, because those stores are remote, you may need to pay high latency in terms of the round trip, so that you also have to maybe consider how you can handle concurrency and all kinds of things to have isolated of stream processors. On the other hand, people have also considered using so-called local state stores, where the state stores can be just co-located with your stream processors as they are reading and writing data from it. It gives you faster access, but also better isolation of your state stores. And then when you take a look at the global view of those states, you can just aggregate each one of those shards of your local states, and you actually have the global state store views. So Kafka Streams took the second approach, where basically when you have those stateful operations such as like aggregate or joins, they will automatically create those state stores locally so that they can be leveraged to complete such operators. And when you have multiple ones of such instances, each one of those topology or instance will have their own state stores that can be read and write and also queried externally. So when I talk about queries externally, this is what I actually meant for that. I think you have a common practice where you will use, for example, a stream processing library or stream processing framework to do your data for like cleanness or enrichment or all kinds of transformation. And you do like aggregations and you dump your results into external systems. And then you can let other applications or other teams in your company to query them. But with Kafka Streams, you can actually have a bunch of APIs that other applications, not maybe built by yourself, can query those state stores directly so that you do not need to necessarily establish those external systems in order to have queries. So I'm not saying that you should not use HBase or Cassandra or Kudu to do all kinds of things. But the point here is that with Kafka out of the box, it should give you these functionalities to do what you need in terms of streaming your data and do real-time analytics, alerting, and monitoring on all kinds of things. So when you actually take a look at the DSL here, you may realize that you have 2 types of first citizen classes in the DSL. One is called the K-stream, where you can read it from, say, a Kafka topic, or you can transform it from another stream. And then you also have a so-called K-table, where you can get from a stateful operations. So what is a K-table here? I want to talk a little bit more, or switch my gears, and to talk about 1 key observations when we design Kafka streams, which is the duality between a stream and a table. So the observation is the following. If you take a stream of updates, and each update is basically saying, okay, for this tuple, this value is updated to, those fields are updated to these tables. You can actually replay this stream of changelogs to build your tables or states from the stream. And similarly, if you have such an evolving states, you can actually reconstruct the stream of changelogs while you are updating your state stores as well. So the state store itself, or the tables, can be actually thought about as a materialized view of your underlying stream of changelog records. So this kind of duality, we call it the stream as actually a changelog of a table, and table as a materialized view of stream has actually been leveraged in the database literature as well already, and we are using this observation to design the K-table and the K-stream as two kinds of different streams. The K-stream interprets as a record stream, where each record is a pure key and value pairs, whereas in a K-table, it is also a stream, but it's actually a changelog stream, where a new record with the same key is treated as an overwrite of a previous record with the same key. So to illustrate that, let me give you two examples of a K-stream and a K-table stream. So the K-stream, you can think about it, for example, as a purchase history, where you have Alice bought eggs, and Bob bought lettuce, and Alice bought milk, right? It's basically a record indicating what has happened, or what are the events in your stream. And K-table, you can think about it as like a profile updates stream. So if you look at one time snapshot of those streams, basically it tells you, for example, in the K-stream case, Alice have bought eggs, and Alice now work at LinkedIn. If you apply more records in those two different kinds of streams, in the record stream layer, it tells you that Alice has bought eggs and milk, whereas in the K-table changelog stream, it tells you that Alice is now working at Microsoft, no longer in LinkedIn. So it's actually an overwrite of a previous record. So when you apply different operators in those two kinds of streams, it actually also gives you two different semantics. For example, if you aggregate on a K-stream, it basically gives you the sum when you see records with the same key, whereas if you have doing a K-table aggregation, it basically gives you the overwrites of a previous value, because it's a changelog stream, so that each newer record is actually not aggregating to the previous one, but overwriting the previous record. And we have operators that allows you to basically do transformations that is actually from a stream to a table, and from a table to a stream here. But remember, a K-table here is really not a table. It's just a changelog stream that can be materialized as a state store. And when you, for example, have updates into your aggregation operators, you basically, as I show you here, let's say if you have a new record from one of your input streams, it will first bypass the join operators so that the intermediate stream here will have a new record appended. And then when you go through the aggregations, it will have a new record that is overwriting the previous record in the changelog stream. At the same time, the state store will also be updated as your current snapshot of the materialized view. So what about fault tolerance when you talk about state stores? So remember that we have this duality between a table and a stream. And we also leverage this observation to build our fault tolerance mechanisms. The idea here is that we, again, use Kafka to maintain your changelog streams while you are updating your states. The changelog streams can be think about as the source of truth of all your updates into your states, so that whenever you have application failed or you need to have some upgrade path so that you need to rolling bounce your stream's application, you can first migrate those tasks to other machines. Actually, the library will do this automatically for you. And then upon resuming your tasks, they will first read from the changelog to restore your current states. And then you can continue the processing from where you have left. And similarly for reprocessing story. Let's say if you have a bug discovered while your stream processing task is running, or you want to update your application logic, like if you are under an A/B testing scenario. all you need to do is to restart a new application with a brand empty state stores and replay your incoming streams as well as your changelog streams. After it has caught up with your old application, you can then do the switch over and continue from there. Okay, another very important concept in stream processing is time. It's basically because in stream processing, you can't have a global view of your data set because it's unbounded. You have to basically have this time notion to reason about the time variance or how you basically handle late arrival data, for example. The two very common concepts of time in stream processing is event time, which indicates when is this event or this key value pair record in Kafka streams really happens, and this processing time, which indicates when the stream processing library, the client, really has processed this record. And why this distinction is important? Well, because you may have out of ordering or you have late arrival data based on different notions of time, right? If you take, for example, the Star Wars series as example, here I would like to use like the event time as the time where each story really happens in the Star Wars world, whereas the processing time, you can think about it as the time when it was really filmed of the story. You can see that there is really an out of ordering in those two kinds of different notions. And depending on which time notion you take in your streaming applications, it may actually give you different results. So in Kafka streams, we allow users to basically associate a timestamp for each of those key value pairs through a class called the timestamp extractor. You can, for example, stamp your record using the current work clock time as your processing time, or you can just extract the timestamp field from the Kafka message as your event time, which is maybe stamped by the producer client when this record is originally created. Or, for example, if your time is in your value payload, you can also extract it in this timestamp extractor APIs to stamp your records. So one important use of those times is when you have those windowing operators. For example, if you are having a running window aggregations of your streams. And based on the timestamp of your records, you may actually want to put it into different window buckets when you do the aggregations. So for example, here, when you actually have a record whose time is indicating it's coming from a late future in your stream, you don't want to actually put it in your current bucket, but you want to actually put it in a very future bucket so that you will have the right examples. And similarly, as you move along, when you have actually a late record from like whose timestamp here is green, actually it indicates it's coming from the history, you can actually put it to its corresponding bucket so that the aggregates, the countings can be updated. Okay, so those are like the hard parts I have covered while you are doing it with a DIY approach, where compared with what Kafka Stream Library can give you. But I would recommend you to read more details about all those technical challenges through our web docs. And again, the key observation here, or key idea here, is that we not only want to make this library to be powerful, but also we want to make it very simple to use. Because if, as a programming framework, programming interface, it is not easy to use, no matter how powerful it is really not a successful system. So that is about how you would process your data in Kafka as long as it become available. But how can you get your data into Kafka if your data is like in other systems? One option you can have is the so-called Kafka Connect framework, which is also included in the Apache Kafka in a recent release this February. It actually is a framework which allows you to program your ingress or egress pipelines from other systems into and out of Kafka in a very easy way. And since it's first introduced in this February, we have actually collected more than 40 connectors coded under this framework from the open source community. And some of them is contributed by Confluent ourselves or our partners, but more are actually from the whole community. They cover systems like MySQL, Cassandra, Elasticsearch, where you can easily use those connectors to basically pipe data in and out of Kafka to those systems. So going back to the big picture of Kafka as a streaming platform, what I want to emphasize here is that as an out-of-box solution, Kafka can actually allow you to basically do all kinds of real-time functionalities, such as piping your data and process them in real time with the system as a whole. Well, I'm not saying that you do not need to have any other system to build a layered architecture, but the whole point here is that with Kafka out of box, it should give you enough functionalities so that you can actually use it as a bare minimum functionality before you consider actually adding more systems having the operations over those. And this, just to illustrate this idea, as I mentioned here, you can use, again, the producer and the consumer clients to basically read data into Kafka or write them. And you can use the Connect framework to pipe them from different data stores. And eventually, you can use Stream client to process them as soon as those records are piped into Kafka. So that will be the end of my talk. So two takeaways. The first takeaway, as I mentioned before, is that stream processing is not necessarily transient or lossy. It's just a new programming paradigm that allows you to process your data as soon as they become available. And with the newly added clients, Stream client into Kafka, we believe that people can now find it much easier to build their real-time stream applications with Kafka. If you want to learn more about Kafka, I would like to recommend you to read the open webinar series about how to build your software stack over Kafka and how to operate them. And if you are already a user of Kafka and are willing to share your experience operating it, we have the coming Kafka Summit series next year. We have 2 venues in New York City and San Francisco. And I would love to hear your proposals about your talks to talk about your usage in Kafka. So that will be the end of my talk. Thank you for your coming. Time for questions?
Right, so you said there's a way to expose the decay tables out to an API for different variables. Can you talk a little bit about what systems connect to that and what handles the query of the decay table?
Okay, so the APIs that we have exposed in Kafka streams is that for each K table, whenever you decide to materialize it, okay, you can have a store name when you basically store that in your state stores. And as long as the other users are aware of the store names, they can leverage it through the exposed APIs to query the running Kafka system application through the store names as the parameters, right? But the first thing is that as long as, again, you have the store names at hand, you can do that.
Fault tolerance and how you catch up to old data and reprocess them. This is a little bit more basic question because I don't know too much of Kafka. How much of data is kept in the changelog, and how do you control that?
The question is how much data is kept in the changelog?
How much of history?
So if you are familiar with like a write-ahead log in database, like war log in database, basically the changelog can be just think about as a write-ahead log in your data stores where each updates is captured as a record or a message in your Kafka changelog topic. So that by just replaying this log, you will have a full view of your snapshot.
My question was, how do you control how much of the history is kept?
Well, in Kafka, there are multiple ways to control how you want to retain your data. For example, you can retain your data by size. Like you want to return like up to 500 gigabytes of their data. You can also retain your data by time. For example, you can say that I want to retain my topics for 7 days, or some of them I want to retain them for even longer. But also, Kafka have a log compaction feature, which basically is used for the changelog topic itself. The log compaction kicks in periodically, which will basically obsolete those old records as long as there's a new record with the same key. So the same idea of how you will basically apply them to override your state stores. So with log compaction, we will basically also shrink the size of your logs.